In this video, we're going to work example problems where we simplify radical expressions. So in the previous section, we learned how to simplify radical expressions where we multiplied two single-term radical expressions. And then also in that same section, we did summing and subtracting of radicals. And then in this last section we just went through, at the end of that section, we talked about multiplying radical expressions, but not just single term, but like multiple terms. So we're going to go ahead and work examples from all of these parts of the textbook here in this video. And so it's really straightforward in terms of like what are the techniques, right, for doing this? Because, okay, if we're multiplying two single term radicals, well, then that just comes down to the properties of radicals, right? So you could think about converting this to the exponent form, and then multiplying it that way. But then you might have to, when you're done, go back to the radical form and then do the whole radical simplification techniques, right? Well, not in this case because there's no variables. Well, maybe in this case as well. Or you could leave it in the radical form and use the properties of radicals. So that's what we would do here, right? So it's the same index. So you can multiply the 10 and the 14. And now we just simplify this. We go from there and simplify this, right? But okay, but if you're not multiplying two single term radicals, well, then the only other cases are going to be where you need to distribute or like combine like radicals. So when it comes to adding and subtracting radicals, it's similar to combining like terms with variables, but you can only combine like radicals. And so this all comes down to all we're using here is the main property is the distributive property. But every number obeys the distributive property. Every number, real or complex, every number in the complex plane obeys all of these properties here. These properties of not just real numbers, any number. And I've said it before, but it's a really, really big deal that anything that you consider a number, which we can think about any number in the complex plane, obeys these properties here. And you might say, well, oh no, these are just like some basic properties. There's a lot more properties that come into play. Not really. Not in terms of what makes something behave like a number. Not really. This encompasses addition, subtraction, multiplication, and division, and distribution, and the distributive property. Okay? So think about it. Addition, subtraction, multiplication, and division. You might say, well, there's a lot more than that. We've been defining all these different operations on variables. There's more than just addition, subtraction, multiplication, and division. Okay. X to the n power. Let's start with a positive integer. What is that? That's repeated multiplication. Okay. X to a negative integer power. Well, that's going to be just repeated multiplication, but then with a division mixed in. Okay. X to the 2/3 or anything, X to the m over n. Well, that's just a radical. A radical is just like the reverse process of an exponent. Like in the same way division is the reverse of multiplication, it's kind of harder to see how a radical is like, if x to the n, it's kind of hard to see exactly how you interpret what a radical is, but it's the opposite of a power. It's like it's some sort of multiplication, I guess, or kind of, I don't know how you would look at it, right? Okay, so what are the other operations we're gonna talk about? We haven't talked about any other operations than this. I guess x to the pi, an irrational exponent, but that's going to be repeated multiplication. Well, we'll talk about later in the algebra textbook of the exponentials and logarithms. Well, what is an exponential? An exponential is just a power term, but it's more like all-encompassing of all of these. It's like you take any number, any base, to a variable exponent. Okay, well, the variable could be rational, it could be an integer, it could be negative, it could be irrational, but it's just a power. It's repeated multiplication. And a log is just the opposite of this. Okay, so it's a really big deal that we can say that all numbers in the entire complex plane obey these properties here. It's a really big deal, because then what that means is you can technically look at any variable expression that you would see in all of algebra in any scenario and think about that could be a complex number, okay? And furthermore, it's like if you don't have to think about, oh, well, am I allowed to do this with any number, like distribute or whatever? Well, no, you can distribute any kind of number. Am I allowed to take this number to a power? Am I allowed to do this or that? You can do anything we learn in algebra. You can do that with any number. The only thing is why this gets confusing is that we're not gonna learn the exact, like, all the nuances that come into play in terms of taking like a rational or a complex number to a radical power, to a rational power, which is a radical associated with it, or a complex number in an exponential or a logarithm. We don't learn that. We don't learn that in detail until complex analysis. That's a complex analysis course. So we kind of shy away from doing problems that involve complex numbers with these kinds of powers in this entire course, because we don't want to get confused. Okay, so but once you're done with complex analysis, then you could take any equation you ever learned in algebra and think about that from the perspective of any number in the complex plane could be the variable. Okay, so just notice as we go through these problems in this video, notice how all we're doing is it's going to be addition, subtraction, where we are applying these commutative properties, associative properties, the distributive property. That's all we're doing. Okay, and notice as you go through the course how it fundamentally any problem you work, anytime you simplify anything, fundamentally you're just using these and only these properties, except for like if you're using exponent properties or stuff like that. They're just properties related to exponents. But again, exponents are at the root of what an exponent is just multiplication. Okay, so. Okay, like here, we need to use the properties of radicals, right? They're properties of radicals, but a radical is a form of like inverse multiplication or inverse exponent, okay? So 140, now we just simplify this, is 10 times 14. Okay, we've got 5 times 2 times 7 times 2. So we can take out a 2, and 7 times 5 is 35. There we go. Okay, we can combine these. We can multiply the radicands because it's the same index. So x cubed y to the third. Okay, now we want to, cube root. Now we want to simplify this, but this is an odd index, so that we don't have to think about if we have to take out an absolute value or whatnot. We don't have to think about anything like that. So we can see this is just going to be x, y. Okay, let's see. 3 times minus 5 is minus 15. And then we can, let's see, the 4th root of a to the 6th. Okay, but now, which is a to the 4th times a squared. Okay, but now, so we've got the absolute value of the principal 4th root of a to the 4th. Do we have to take out an absolute value? Well, no, because in the first place, a couldn't be less than 0 anyway. You see? Right? So a couldn't be less than 0, so it can't be less than 0 here. So no, we're just going to take out an a. Okay, but we're not done because 2 is divisible by 4. So we can see that if we write this in exponent form, we can simplify. So what we're left with is, and there we go. Okay, so minus 1/2 times 4/3 is going to be minus 2/3. Okay, and let's see. Now we can multiply these two radicands. So 6 times 4 is 24. Then a to the 4th, b squared, c cubed. It's an odd index, so we don't have to think about absolute values. So 24 is 6 times 4. 4 is 2 squared. 6 is 3 times 2, so 3 times 2 cubed. So we've got minus 2/3 times, we could take out a 2. And well, what else can we take out? We can take out an A and a C. And we're left with 3AB squared. Okay, so we've got minus 4/3 AC, principal cube root of 3AB squared. Okay, so now here we're subtracting radicals, and remember we understand like terms when it comes to variables, but it's the same idea with radicals. Even if so, these radicals have variables in them, but even if we had radicals that didn't have variables, right? You still look at the idea of, do you have like radicals? And it's similar to variables. It's just the whole radical with the radicand and everything, it all has to be exactly the same in every way. The idea is, if we picked a value of y, right, and we plugged it into the different radicals, you have to what's going to result is the exact same number. Like that's the whole idea. These have to be the exact same number. And if anything is different in any way, the radicands are different, whatever, it's different numbers. At least maybe in some special cases it's the same number, but like as far as we could input any y, any real number, any whatever complex number, and we're going to get the same number. And that's what means that like means. So now, since these are, but the coefficients don't matter, right? So the coefficients are different. That's fine. So okay, so minus 9, or 3 minus 9 is minus 6. Minus 6 plus 1 is minus 5. Okay, and then there we go. Okay, we don't have any like radicals here, but we can simplify and see if once we simplify, do we end up with some like radicals. So 50 is 25 times 2. 18 is 9 times 2. 72 is 36 times 2. So, okay, we can take out a 5. 5 times 1/5 is 1, so we're left with root 2. We can take out a 3. 3 times 7/3 is root 2. We can take out a 6 here, and we're left with... Now we have like radicals. So 1 minus 7 is minus 6. Minus 6 plus 5, minus root 2. Okay, yeah, here we don't have any like radicals, but let's simplify and see what happens. So, okay, so 16, 8 times 2. Yeah, 2 to the 4th is 16. So we've got 2 cubed times 2. So we can take out a 2. We don't have to worry about absolute values. We can take out a 2. So minus 3 times 2 is minus 6x, and we can take out a y. And we're left with what? 2xy in the radicand. Okay, 54 is going to be what? So 27 times 2, and then 3 cubed is 27. So 3 cubed times 2. So we can take out a 3. 3xy, and then we're left with 2xy in the radicand. Okay, now 250 is 125 times 2. Now 5 cubed is 125. So 5 cubed times 2. So we could take out a 5. 5 times 5 is 25. Oh, and then we could take out an x and a y, and we're left with 2xy. So now we have like radicals. Same index, same radicand. But look, the coefficients, oh, well, we have like coefficients as well. So what is it? So great. Well, no, remember that, yeah, it's the coefficients are like as well, which is nice. But they didn't have to be. It's not like if we had variables out here, if this was an xy squared, this was an xy cubed, that, oh, well, now these aren't like anymore. No, you would still just sum the coefficients. You just couldn't combine them. You still have like radicals. Okay, but we do have these like coefficients as well, so that's kind of cool. So we can just say minus 6 plus 3 is minus 3. Minus 3 minus 25 is minus 28. And then just... there we go. Okay, yeah, here's a good example, right? Oh, well, no, these aren't like this. This is fully simplified because we don't have look, it's not like terms here. We got a y here. Well, no, the radicals are like. I mean, I guess maybe this is not simplified if you think this is cleaner, but no, the radicals are like radicals. So you can do this. We can it's confusing because I don't want to call 5y a coefficient because it's not a constant, but with respect to the radicals, it kind of is. So no, we can write 12 plus 5y. We can't combine it, but we can do this. We could do that. Now, maybe you would argue that this is more simplified, but just saying that these are like radicals. Okay, these aren't like radicals, but let's see what happens when we simplify. So 98 is 49 times 2, so 7 squared times 2. Okay, now these are even indexes, so maybe we have to take out an absolute value with like one of these variables here. So 8 is 2 squared times 2, but z can't be negative anyway because like it's z cubed, z, so we don't have to worry about an absolute value. So we've got minus 1/2 times 2 is just 1, and then we're going to take out a z. And then we're left with 2z in the radicand. Here we take out a 7, and we're left with 2z. Now we have like radicals. So we could do 3 minus z. There we go. Okay, so now this is a little bit different because we've got these multi-termed expressions here with radicals. It's just distribute. You don't have to be distribution works for any number in the entire complex plane. So if you have a complex number, whatever, or if you've got a variable and you're thinking, oh, well, if this represents if this could be a complex number, I can't distribute. No, you can do whatever you want with it. Remember, real numbers are in the complex plane. Okay, so if a real number can do it, then so can a complex number. The only reason you might have to that you might not be able to do something is because there can be certain caveats to working with complex numbers that aren't there when you're working with real numbers. Like to divide complex numbers, well, because complex numbers have this different form. It's like this two-part form. It's different than. There's some subtle differences. Oh, well, this we can just change to 3. Well, here we have to do something different that we'll learn later. But it's all you're using. They're all numbers. What we're going to have to do to divide these is going to be multiplying this by like 1 in the form of something, and then going from there, like in the distributing, etc. They're all numbers. So just distribute, right? It doesn't matter that it's a radical. Just distribute, and then what do we when we distribute? We've got we have a single term radical times a single term radical. We just did a bunch of those problems. We have another single term radical times another single term radical. We just worked those problems. So it's all straightforward. Okay, 5 times 2 is 10. Root 2 times root 2 is 2. 6 times 5 is 30. 3 times 2 is 6. 5 times 4, negative 4 is 20. Okay, so 20 plus 30 root 6 minus 20 root 2. There's nothing more we can do with this. These are not like radicals. So that's it. Okay, 5 times 3 is 15. 6 times 3 is 18. 3 times minus 4 is minus 12. 6 times 2 is 12. And then 3 times 6. Root 6 times root 6 is 6. Note that when you have like a square root times a square root with the same radicand, the radical just goes away. But that's not a universal thing. Like if you've got the cube root of 6, the principal cube root of 6 times the principal cube root of 6, it's not like, oh, well, the radical just goes away. That just works out with square roots because 1/2 plus 1/2 is 1. Here, 1/3 plus 1/3 is 2/3. So this would be 6 to the 2/3. That would be 6 squared. So that would be 36. And so could we simplify that? 6 times 6. So 2 times 3 times 2 times 3. No, I mean, that would be it. Okay, so 9 times 2 is 18. 4 times 3 is 12. So take out a 3. 15 times 3 is 45. root 2. Okay, take out a 2 here. 12 times 2 is 24. And then 18. There we go. Okay, let's just distribute. So 2 times 4 is 8. Root y times root y is y. 2 root y times 5, you've got 10 root y minus 12 root y minus 15. Okay, so 8y now minus 2 root y minus 15. There we go. Okay, let's just distribute. So 6 times 4 is 24, and then times root 3, it's just 3. Okay, 5 times 4 is 20, and then root 15. Minus 2 times 6 is minus 12, root 15, and then minus 10, and then times 5. So 24 times 3 is 72, and then we have like radicals here, so plus 8 root 15, and then minus 50. So 72 minus 50 is 22, and then there we go. Okay, 2 root 3 times 2 root 3 is going to be 4 times 3, so 12. Then minus 2 root 21. And then plus, well, yeah, these are conjugates. Okay, I mean, we could have just multiplied it out. That's fine, but it's good to recognize when you've got conjugates. You see, if 2 root 3 is a and root 7 is b, you've got a plus b times a minus b. So it's just going to be 2 root 3 squared is 4 times 3 minus root 7 squared. So 12 minus 7 is 5. Yeah, look, we have conjugates again. If a is 4x root y and b is 2y root x, then you see it's a minus b times a plus b. When you're multiplying conjugates, no matter what it is, any kind of variable, again, this is all, how did we develop conjugates? A was any number, B was any number in any kind of variable expression, any placeholder for a number in the complex plane, any number. Remember, real numbers are in the complex plane, any number. Well then, okay, so, all right, they're any number. Well, all we're doing here to develop this formula is distribution and multiplication and addition, and etc. Well, okay, so any number, you can do this with any variable, any number. So a squared is 16x squared times y. B squared is 4y squared times x. And we can't combine those anymore, so there we go. Okay, so here they want us to think about that perfect square trinomial, but you don't have to memorize that. You could just distribute, just write this out and distribute it. But so if this is A and this is B, then A squared is 36z squared, and B squared is 5. So the perfect square trinomial with a minus, like A minus B squared, is going to be A squared minus 2 times A times B. So 36 times 2 is 72. And then 72 times, or no, that's not, I'm sorry, that's 2 times A times B. So that's going to be 12 root 5z. And then plus B squared. And there you go. Okay, so yeah, like we could do, if this is A and this is B, then again, you don't have to do it this way, and you don't have to memorize the perfect square trinomial form, but like we've got A plus B squared, okay, which we know is going to be A squared plus 2AB plus B squared. So what's B, or what's A squared? Let's start with A. What's A squared? That's 25A to the 4th B. What's B squared? That's 49B to the 4th A. So what's 2AB? A is, so 5A squared root B times 7B squared root A times 2. So 5 times 2 is 10. 10 times 7 is 70. then a squared b squared, and then root ab. So, okay, a squared plus 2ab plus b squared. Okay, yeah, we've got conjugates again, right? So you could say a is square root of x plus 1 and b is 5. And you see it's a minus b times a plus b. So what is a squared? X plus 1. Then minus what is b squared? 25. So x minus 24. That's it. Okay, so we could use the, I mean, let's not use the perfect square trinomial formula. Let's just do it ourselves. So okay, so square root of x plus 1 times square root of x plus 1 is x plus 1. And then we're going to have minus 5. Let's see, minus 5. And then minus this again. And then plus 25. Okay, so we've got x. And then we have, so minus 10. And then 1 plus 25 is 26. Now, this is kind of weird because it's like, well, wait a minute, this is b squared. Well, no, it's because when we squared a 1 came out. So when we simplify, we get something that's going to be, it'll be hard to recognize the perfect square trinomial form here. It'll be really hard because you don't even see the first term isn't squared. So, but yeah, there it is. Okay, so yeah, this is a little bit different because, well, okay, we are kind of multiplying conjugates inside the radicand. So if a is equal to 5 and b is equal to 2 root x, then we are doing a plus b times a minus b, at least inside of the radicands, right? Because we can combine these radicands. So a squared, 25 minus b squared. So what we're going to get is this, 25 minus, and that's it. We can't go any further than that. Okay, so let's just multiply this out. So okay, all right, square root of x plus y times square root of x plus y is just x plus y. Then we're going to have, let's see, yeah, this is kind of weird. So the square root of x plus y times minus the principal square root of x minus y, we can combine those and multiply the conjugates. So it's like it's like this. It's like we have minus, and then we've got this times, right? Well, we can combine these, and then what's inside the radicand, you multiply the conjugates, which is going to be x squared minus y squared. So with just a minus out front, we're left with like that, right? And then you'll do the same thing. You'll get the same exact result here with the next multiplication. And then we're going to get plus, and then x minus y. Okay, so x plus x is going to be 2x. Y minus y is going to be 0, and then we're going to get 2. And there we go.